Okay, all right, let's get started with today's class. So again, the first thing is the labs. All right, so we have intro next week. This is not the full lab, but this is basically just the lab introduction. This lab introduction. So please go to your sections for the lab introduction. We'll take about 20 minutes or so just to make sure that you can run the software. So the installation instructions and where to find the software and all that thing is on the class website, but make sure you install it before next week when your section starts. The reason is once you install the software, you actually have to send an email to somebody for them to activate for you. That takes 2 hours turnaround time. Okay, so it's not, you cannot do this in real time. So you want to make sure at least you try to do this as, let's say, a day ahead of your lab section. All right, so it's fair. So we tried it. The TAs tried it. I tried it. Seems to be fairly straightforward, both on Windows and Mac. So you should be able to get it working. If you can't, then definitely email the TAs to let them know. Again, for groups, you can find your own groups or wait until the section. TAs can assign groups for you. So again, we're looking for groups of 2 or 3. Any questions about the lab? Okay, so we're looking to do the lab, as synchronous as possible, right? So, so if you have some conflict with this lab section you're in right now, just email me to let me know, and we can switch you around, right? We can switch which lab you're registered to, right? But just let us know. We can do that. Okay, all right. So then let's look at do a brief review of what happened last time. All right. So last time to recap. Last time we talked about power, right? So last time was all about talking about the power produced or power consumed in your circuit. And what we got to was you want to look at something called a complex power. Right? So the complex power, denoted S. This is P plus JQ. P is the active power. Q is the reactive power. Right, and this is given by the equation of V as a phasor, I as a phasor star, and this star is on there's a complex conjugate of the current. Right? So the math works out this way for this to be the complex power equation. Okay? So most of the time, our calculations boils down to computing the voltage, computing the current, then doing this multiplication, and then figuring out, and then trying to figure out what the real and imaginary part of the complex power is. So as as a question earlier in this class, what we asked is for phasors, V bar, the magnitude, right? The magnitude of this phasor, or let's say if you write a phasor V bar as V angle, some angle of voltage, then this V is always the RMS value. It is always the RMS voltage. Otherwise, the power will not work out correctly. Okay, so it's RMS voltage. You divide by this √2. It turns out this √2 also works out correctly when you talk about power as VI star, okay, as VI conjugate. So remember, the magnitude of all the phasors are RMS values. So if you have questions, just ask. Sometimes it's hard to monitor. Yeah,
I just don't like to just cut you off when you're talking.
No, it's fine. Please cut me off. Otherwise, it's hard to monitor chat. And so yeah, just please go ahead.
So obviously Ohm's law, V equals IR. So then in these situations, R is replaced by Z. So when you do like I conjugate, can you replace that with V over Z? And if so, would that be V conjugate and Z conjugate, or?
Right, that's a good question. That's a good question. So I is V over Z, both are complex numbers. So when we take a conjugate, you conjugate every part. You're gonna conjugate every complex number you see. Okay, so that's a definition. That's a conjugate. As you go into the equation or go to the number, every time you see a angle, you flip to negative sign. Or every time you see a J, you flip the sign. So you conjugate every part. Conjugate both. Yeah. Okay, right. So that's a good question. Yeah. So you conjugate every part. Okay, so this is our equation. So let's do some examples to get a feeling for these things. Okay. So the first example, let's see how much space I have. Okay, so let's say we're given some time domain signals. Say 150 sine 377t plus 0.2 volts. So that's our voltage. Our current is 25 sine 377t minus 0.5 amps. Okay, so these are our voltage and current. Let's say we want to find active and the reactive power, right? When you have this kind of voltage and this kind of current. So for those type of questions, the first step is always convert them to Phasor form. Okay, so in this class, in the vast majority of power systems or energy systems, we very, very rarely look at any time domain signals. Very rarely. Where you see the sort of sign of something T that comes out. Okay, so most of the time, as you just work with phasors, so everything is in phasors, we directly do complex algebra on the phasors. So the first step is always convert them to phasors. Okay, so the voltage phasor, remember, divide by square root of 2. Okay, this is the RMS value, always divide by square root of 2. I cannot emphasize this enough that again, a significant part of the grades that lost on the midterm is some people forgetting to divide by root 2. Okay, so please divide by root 2 to get RMS value. And this has angle 0.2, right? We don't care about the frequency. So we have the angle of 0.2. Now, one thing to be careful is about the unit of the angle. So if I write it like this, what's the unit here for 0.2?
Radians.
This is radians, right? This is radians. So if I don't, this is radians. But then it will depend on your calculator whether the default is radians or degrees. Right? And also sometimes the question uses radians, sometimes the question uses degrees. Right? So it's just something to be careful of. So one way to do the problem is always convert things to degrees. Okay? So one way to do it is just convert things to degrees. So we can convert this to degrees. Let's say 106.07 angle 11.46 degrees volts. Okay? But it's often safer to just convert everything to degrees and remember that. But if you use a calculator, for example, to do those type of questions, then be sure you understand the degree and understand the unit your calculator is using for the angle. Okay? Understand that unit, right? So if your calculator likes to use radians, then make sure it's in radians. Your calculator likes degrees, make sure it's in degrees. And for this, for this class, you can use your computer if you want, but also make sure whatever program you're using treats the unit of the angle consistently. And as a convention, most of the time the angle are given in degrees for us, just as a convention. We like angles in degrees. But when you're doing your calculation, just make sure they're consistent. Make sure whatever radians or degrees, use the same unit for your angle. So this is the current, 25 divided by square root 2, angle minus 0.5. So I can also write this in degrees, 68, 28.65 amps. So now when we find the power, this is pretty easy, right? Our power is complex power. Star conjugate this. So this is 106.07 angle 11 degrees times 17.68. I'm conjugating this, so I flip the sign on the angles. You multiply this, we get 1.434 plus J 1.208 times 10 to the 3. All right, so this is our complex power. Simply, you just multiply these two complex numbers together, you get some result. So this has a unit of volt amperes, volt amps. Then if you want to talk about the active and reactive power, just reading out the real and the imaginary part. So this is P, this is Q. P is 1.434 kilowatts, right? KW, kilowatts. Whereas Q has a different unit, kilowatt amperes. Oh, sorry, kV reactive, right? kVA reactive. Okay. So this is just a standard type of questions. Any questions about this? Okay, the thing to pay attention to is just the angle, or just a unit of the angle. Make sure your calculator is interpreting the angle correctly. All right, so then we can do more. So let's work through a more, a little bit more complicated example. So here we're given a circuit, right, with source voltage, and then we want to understand the power flow in the circuit, right? We want to understand how much power is coming out of the source, how much power is being consumed by the load, what is the power loss in the line. So here we want to find load impedance, we want to find the current, and we want to find, let's say, the power consumed by the load, this power lost in the line, and then the source power. So let's say we want to find all these quantities. All right, so this is a standard circuit analysis we have. So this is a fairly standard question, you'll see. And then for this type of question, the first step is to find impedance, right? So the impedance is we have a parallel circuit between the inductor and a resistor, and we find this impedance Z. Okay. So the same equation works, right? So the impedance for complex impedance, the equation works exactly as when you have real numbers, we have just resistance. Okay. So the exact same equation works. This is 1 over R plus 1 over JXL. Because the exact same equation as before. This is 1 over 20 plus 1 over J times 10. When you do this, you get 4 plus J8 ohms. Okay, so the unit is always ohms, even for a complex impedance. The real and imaginary part have the same unit. Right? We don't differentiate the unit here. Although for power, we do differentiate between the real and imaginary part. For impedance, we just call both parts ohms. We do not differentiate between these two parts. So once we find the impedance, then we can find the current, right? We can find the current. Okay. So the current is given by voltage over the total impedance in the circuit. Right? So the total impedance, just the line impedance plus the load impedance. We can add them up. So this is 1 plus J5 plus 4 plus J8. We get 5 plus J13 ohms. Right, so this is our total impedance. Now for voltage, here is given that the voltage is 110 volts, 60 hertz. Then what is the phasor then, right? So I need to translate to a complex number. So what is the phasor here if I tell you the source is 110 volts and 60 hertz? What's the magnitude, what's the angle? So what's the magnitude? Do I have to divide by √2 here?
No.
No, right? So this 110, whenever a voltage is stated, it's assumed to be RMS unless explicitly said otherwise. Okay, so if you see a statement that says the source is 110 volts, that means it's 110 volts RMS. Okay, so that's always the convention. Vast majority of the time, it is RMS voltage. So that's without stated, it's assumed to be RMS. So that's the magnitude. How about the angle? What angle should I assume the voltage to be?
0.
0, right? So we can take, angle is always reference to something. So we may just well take the angle reference to be 0 at the source. So we'll take this angle to be 0 degrees. We can divide by 5 plus J13. We get a current that's, so you can either keep this in polar coordinates or in rectangular coordinates. Here, I'm going to just write it in polar coordinates, 7.9 angle minus 68.96 degrees. Yes.
So elaborated back on that, not to go into too much detail
Right.
because it's one of the homework questions, but so like if we're doing VI cosine theta or VI sine theta to find the real and reactive parts, when we do those calculations based on what you just said, V and I, we just pull the magnitudes. You aren't dividing those by √2, correct?
Yes. Wait. So which homework question are you talking about? Let me try to make sure I give you the right answer.
I want to say, I think it was question 5. I can grab my notes real quick. It was, we got the RMS voltage of like 120, and then it asked to calculate the real power. Yeah, so part 2 of question 5. So we go through and find the source current for part 1, and then the part 2 asks us for the real and reactive power. So I did the VI cosine theta and VI sine theta, and so you just take the magnitude from the phasor since you have the VS is given as a VRMS, so it's just the 120, and then we use what we found for the source current, but we don't divide those by √2 again.
No, you do not. You do not divide by √2 again. You do not divide by √2 again. They're already RMS. Yes.
Thank you, sir.
Yeah. So for that question, you can either just multiply the current conjugate, or you can do VS cosine theta over sine theta. That's the same thing. It will work out to be the same solution. Yeah. Okay. So yeah, it's rather similar to this question. This example a little bit more complicated, right? So I find the current. Now next, let's find the load voltage. Okay, let's find the load voltage. So the low voltage, again, Ohm's law still works, right? So you have current, this much current going through a load with impedance Z. Low voltage is still IZ, okay? Current times impedance is the low voltage. You plug this in, degrees times 4 plus J8. We get our load as 70.63, angle minus 0.2 degrees. Okay, so this is our low voltage, right? So we'll come back to this low voltage later. But then once we have the low voltage, we can pretty easily figure out what the power is, right? We know the current, we know the voltage, so we can directly compute the power consumed. So here, for example, we can do the S of the load, complex power consumed by the load. This is V load times I conjugate. Plugging the numbers, we get this is 249.36 plus J 498.44 volt amps. Right, so this is just the complex power consumed by the load. You can read off the real and the reactive power if you want from the solution. Any questions so far? Right, so for sure you'll get a question like this on midterm. This is sort of a very standard type of complex power calculation that we do. The next is, how do you compute the, say, the power loss on the line? Right, so how do I compute the power that's consumed by this component? This 1 plus J5. Oh.
Just the same thing. We already know the current, and then we can use that impedance.
Right. So we already know the current. We can calculate that impedance, right? So we know the power loss on the line. This is I, right? So this is the magnitude of the current squared times the real part, the resistance part of this line. So this is I squared times 1. So this R loss is 62.4 watts. Then we have a reactive power loss. This is I squared times the X part of the line, I squared times 5. So 5 times as large, right? So this is 321.05 volt amp reactive. So then to find the source, right? So we have P from the source. This is just P load plus P loss in the line. This turns out to be 7 watts, and Q source, same thing, Q load plus Q loss. You add the two numbers together, you get a 10.5 VAR. Okay. So if you look at this calculation, it's basically you're actually providing something more reactive power than active power. Okay, you're providing, so the loss is dominated by reactive power. The load is actually dominated by reactive power. You're consuming more P than Q. So the consequence of that is actually your voltage is quite low. Okay, so this is a low voltage. Your voltage is quite low because you're, right? So what's happening is, remember, by Ohm's law, the voltage difference drives current flow, right? So I need to supply a lot of reactive power, so I need a big current. So I need a big voltage difference. Then my load voltage needs to be low, right? To create a large load difference, to drive large current flow, because a lot of this current is carrying reactive power. So that means I'm suddenly, right, facing with a low voltage at my low side. And this is not great. So it's most appliances, most loads are designed to operate within some voltage range. And often 70 volts is too low. So I don't think your computer adapter will work when the input voltage, for example, is 70 volts. Okay, so this is a low voltage problem. And to see why this is created by the large amount of reactive power, so let's do the same calculation. But then now say, I somehow canceled out the reactive part, the reactive part of the impedance. Okay, so remember before we had an inductor that's 10 ohms. So now let's say I got rid of this inductor, everything else being the same, and let's see what happens here. Any questions? Something down? Okay, so our goal is to see, right, if I have a very low voltage, here is to demonstrate that low voltage often comes because you're carrying too much reactive power in the system. Okay, so here we remove the inductor, which in practice will be canceled out by installing a capacitor. Right, so that's what happens in practice. But let's say mathematically it's equivalent to say I got rid of that inductor. Then let's say we repeat the same calculations. Okay, let's just repeat the same calculations again. All right. So here now when we repeat the same calculation, we still want to calculate the current, the low voltage, the power consumed by the load, the power loss, and power sum, and so on. So here my Z total, my total impedance. Since my load is purely real, this is just 20 plus 1 plus J5, 21 plus J5. Right, this is my load impedance. My current now is the source voltage divided by Z total, 110, angle 0, 21 plus J5. This comes out to be 5.09, angle minus 13 amps. Okay. So now let's look at what the load voltage is. So now let's look at this low voltage. Now V load is I times Z. So here what we get is 101.8 angle minus 13 volts. So this is a much better looking voltage, right? Your device will not complain about this voltage. Okay, so this is a much higher voltage. So this is good, right? We boost the voltage. And then let's see, look at the power consumed, right? The power consumption. So here the power of the load. This since I only have a resistor, so this will be I squared times my load. This will be 5.09 squared times 20. This is 518.16 watts. My Q load, this is 0, right? I only have a resistor. There's nothing consuming reactive power in the load. And then we can do the same calculations again. I can do the loss, the real power loss. This will be 25.91 watts. Q loss. This is 129.54 volt-amp reactive. Then you can add all this together to figure out the source as 7 watts. The reactive power coming from the source is 129.54 volt-amp. Okay. So this calculation shows that if you get rid of the inductor, or you get rid of a lot of the inductive part of your load, your voltage is higher at the load, and you can deliver more active power with lower loss. Right? So compare this active power, you're delivering about 500 watts with a loss of 25. Or here you're delivering 250 with a loss of 62, right? So you boost the voltage, more power, lower loss, right? This goes back to why you want voltage to be reasonably high for translation. Any questions with this calculation? Okay, so that's why we'll do the power factor correction. But by power factor correction means that we get rid of a lot of the inductive part. You want to get rid of this inductive part. So basically, we install XC or install in parallel, and the goal is to cancel out XL, right? The reason again that you can add and subtract things like this is because reactive power is again just oscillations, right? So I can cancel out oscillations. Right? So you cannot do this trick, for example, with resistance because you don't have a negative resistance. But for inductance or capacitance, you can add and subtract. They can cancel each other. But normally, this is what we do: is we add a big capacitor close to the load to reduce the current flow in the line, to improve the power factor, to lower loss, to compensate for voltage. So this is often called reactive power compensation, or voltage regulation, or power factor correction. There are a lot of names for this. And you do see this. And when you actually look at it, you see this, right? So if you look at all these devices, this happens here. You have capacitors. And when you look at this kind of devices, you have capacitors. But physically, they're on the poles, they're close to ground, they're in substations. This is done very often to boost voltage. Any questions about this? Right. So again, this is actually a fairly common principle in circuit design. As anytime you have problems, add a big capacitor close to the load. It solves a lot of problems. Okay. Right. So let's think to transition us from now. We're talking about AC power. Next, we want to transition to power electronics. So to motivate us to think about power electronics, as we can think about this power factor correction or voltage regulation or reactive power compensation a little bit closely, right? A little bit in more detail. Okay. So if you look at the load, right? So typically a line goes like this. We have a load here. So I'm going to just draw this to ground. And then we add this capacitor to compensate for reactive power. So the question for us to think about is the value of the capacitor fixed, or do I have to adjust the value of the capacitor? Right? Do I want to just install a capacitor and be done with it, or do I still want to adjust this? And then that we just always install one capacitor and be done with it? Or do you think that the capacitance value of the capacitor has to change from time to time?
Probably needs to change based on the load.
Right, you need to change based on the load, right? So load changes. So one specific capacitance will not work, right? So this is similar to impedance matching I saw in the chat, right? So your load changes. The load value, the P and Q of load changes. So you cannot have a fixed capacitance. That will also create problems. Right, having too much reactive power is also bad because something has to consume that reactive power. So your voltage cannot be too low. Your computer will device will complain. A voltage that's too high, your device will also complain. It won't work. Okay, so you want the capacity just right, right? So then how do I change this capacitance? I said load as time varying. Right, so load changes from time varying. So load changes time to time. So normally the load change is something like, this is our load change over a day. So time, this is load, think of this. So now I need a variable capacitor. Right? So normally the way you design a variable capacitor is the following way. You start off, you have a capacitor. You have many places like this. You have many places like this to ground. And then you have a tap. And this is called a tap. And this tap will connect to one of these, right? So this is called a tap changing transformer. What this does is basically by changing which one it connects to will change the capacitance. Okay, so there's a switch and there's a mechanical arm that moves across, right? That moves across this different capacitance, and you pick out the right one. Okay, any questions so far? Okay, so this is our tap changing transformer. So how many times do you think this will change per day? So you have, that's right. So remember this actually is a mechanical device, right? You think of place like this, then the arms are that moves and connects to different ones. And if you stand by substation, you actually hear this. You hear this click, 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 click of this thing switching through. Right? So it's sort of a bulky mechanical device. So this will switch a few times a day, right? A few times a day. And this has a lifetime of, let's say around 20 years. Right? So you buy this type changing transformer, this is not cheap, but then, and now you don't have to use them many times, right? You don't have to use them that much. Okay? This operates, let's say, 4 or 5 times a day, depending on what time of the day. A lot of times when it switches, it's actually hard coding. So you'll switch at 10 a.m., you switch at 5 p.m., things like that, hard coding. So this is how things work today. But do you see any challenges with this methodology once we have, say, a lot of solar or a lot of storage or a lot of electric vehicles? Let's say you have a lot of solar. What does the load look like? Now this sort of very smooth changing. If you have a lot of solar, what does the load look like? Right, so it's unpredictable. It also varies a lot. Right, so you have lots of solar, let's say. Okay, so that becomes something like this. Okay, so I'm just drawing this as, for example, solar. Right, some random, very fast changing solar. Now, if you still want to use a tap changing transformer, okay, then how many times do you have to change the tap? Right? You have to change taps very often. Right? So this requires frequent tap changes. Right? Because I'm trying to follow the load. So my load changes, I'll change the tap. Load changes, I'll change the tap. So my load changes, 50 times a day, my tap has to change 50 times a day. And then what happens to your transformer? If you're supposed changing 4 times a day, it changes 40 times a day. So your lifetime goes from 20 years to 2 years, okay, which is not good. Nobody wants to switch out a transformer after 2 years. Just we don't, our utility will run out of money if we need to buy a new transformer every few years. Okay, so this is very high stress. on the transformer, right? On the very high stress on the transformer. So this is not a desirable strategy, right? Our tap changing transformers were not designed to compensate for something that changes, say, every 5 minutes, like solar. And it's also not designed. For example, if you randomly plug in electric vehicles throughout the day, it's not designed to handle those kind of big variations on the low, very frequent variations on the low. So the way to do this is to go away from mechanical devices. Mechanical devices are fundamentally limited by their mechanical stress. So the way to do this is basically look at solid state devices. That is power electronics. So we'll finish with the AC part of the class after this review. And then next we'll go to power electronics. So before we take the break, any questions? Okay, all right. So yeah, so you can hear a lot of things in the substation. So you ever get a chance to go to the substation? Actually try to hear a lot of those mechanical devices. Quite interesting. So just by the sound, you can tell what's operating. Right? So now let's take our break. So we'll come back at 3:25 and we'll start on power electronics. Okay, thanks. This we won't cover now. Okay, so let's get back to class. All right, so following up on what we said before the break, controlling power using mechanical devices, right, before electronics is quite challenging. So it's inefficient. It's slow. And sort of heavy equipment. It's really not really not easy, really not easy putting in mechanical switches for high power applications. It's not that simple. All right, so we have, nowadays we have electronic switches, which really making things much simpler, right? Much easier to do. So one note is that our electronics components are almost always still discrete. Okay, we do not have something like integrated circuits, right? So we do not yet. So the power circuits are not yet something like VLSI. Okay, still very much discrete components, right? Discrete transistors, discrete diodes, this kind of thing. Okay, so this is still components. There's not integrated design. Right? So you don't need that many of them anyways, right? So you need a few discrete components, right? So that's one thing to keep in mind between, say, power electronics and circuits in the more traditional sense. As power electronics, in addition to the difference in power level they handle, in power electronics, still much more about topology, discrete component design. Whereas in VLSI, it's all about integrated circuits, right? We have many transistors that happens. For us, we have a few at a time, right? So not that many transistors. The applications, nowadays you don't have to, think about applications. Basically, everything requires some power electronics, okay? And everything nowadays requires some power electronics. So you have electronic devices. For computer, phones, TV, things like that. We have motor control. And we have variable speed drives. You may want this. Electric vehicles is definitely one big component. Storage, solar, Also, wind is actually right now heavily power electronics based, and many things going on. Right? So it's really important to understand how these interfaces work. So the goal of this class is to give you a fairly broad overview, fairly high level overview. And then you can go and take many other classes that focuses much more on power electronic design. Right? So here we want to understand from very high level, not including a lot of details. Then later you can go to a lot more details about filtering, packaging, things like this. Right? So for us, we'll start with a basic component, which is the switch. So often when you do look at electronics, the goal is to engineer a good switch. And for switches, what you often what you want to see is this IV curve, right? You want to see this kind of IV curve when we talk about this kind of components. So this talks about the voltage on the switch, and then this talks about the current that goes through it. Okay, so I want to understand how much voltage versus how much current, how much voltage versus current. So then what this switch allows us to do, this ideal switch, is if the switch is closed, right? If the switch is closed, then you can have, right, so this is, all right, so let me draw the open first. Okay, so this is open. What happens when you have an open switch, there's no current or zero current flow. You can have, you can handle large voltage, arbitrary large voltage across the switch. Okay, so this is for open switch, there's no current flowing, but there's some voltage across a gap across your switch. Then when we have a closed switch, this is what happens when we have a closed switch. Here is no voltage drop. You don't have any voltage drop, but you have, current flow. This is what an ideal switch is. It's basically a 0-1 toggle between open and closed. Okay. Any questions about this? Okay, so if you just draw this again, right, basically what you will see is for currents through the switch, if it is open, you get, all the current can flow, but no voltage drop. If it is closed, the voltage is very large, but there's no current. So this is a fairly straight. This is a very unique IV curve. Right? This is just a voltage current curve for ideal switch. And this is quite useful. This is quite useful because whenever you have a switch, it gives you a lot of control for things like voltage and current. Right? Ideal switch is really useful for control. Because what you can do is, let's say, let's say I have a source, a DC source. So there's some VDC, DC source. Then I have a switch, right? And add a load on back on here, add a load here. And then you can operate in two states, right? So this is again, this is for a closed switch. So this is called on state when the switch is on, or it's closed. It's called off state. This is called off state when the thing is open. Right? You basically have no connection. Right, so this is called on-off. Called on-off states. Okay, so T on means that means that your switch is closed, current can flow. Off means your switch is open, there's no current flow. But what this gives you, actually, this gives you a pretty good control for power and voltage. Right, this give you fairly good control already for power and voltage. For example, if you draw out the axis of time, let's say this is voltage. Voltage, let's say at the voltage at the load. Then as you switch on and off, what happens is you can get this kind of square waves, right? As you can get this kind of square waves. Here you're turned on, so at this time we have this on time called T on. Here we're turned off, so this is T off. We call T off, right? And we have a period called tau. Right? So over the period, some part of it is on, some part is off, and the total period is tau. Okay, so we have T on plus T off equals to tau. Any questions so far about terminology on and off and tau? Okay, so this we can turn on and off, right? Then you can look at what is my average voltage then? I'll look at, let's call this average voltage V, right? Let's call this average voltage V. Then what is my average voltage? What is my average voltage here? So let's say the peak here is VDC. Then what is my voltage as a function of VDC? My average voltage a function of VDC. What is V average? Right, so it's not directly over 2, right? So I want to say that T on is not necessarily equal to T off. It's not that you're on and off, each half the time. Right, so can we write this V average as some function of VDC? What is the term in front of this VDC? Okay, right. So we're on for time T on, we're off for time T off. Then what is my average voltage in this case? Right, yeah, so this is correct, right? This is just T on over tau, right? This is just the amount of time I'm on, proportion, the fraction of the time I'm on, right? So if I'm on 40% of the time, I'm 0.4 of the DC voltage. I'm on 80% of the time, I'm 80% of DC voltage. Okay, so this is a pretty easy to change the voltage, right? Pretty easy to change the voltage. So this is similar for power. So we have the power, the average power is simply the amount of time you're on times the power of the source, right? So times the DC power you would have drawn if you had no switching. So this is quite useful. This switch is quite useful. The reason is, for example, if you have a charger, right now there's, let's say you have a USB-C charger. It could charge your phone, could charge your iPad, could charge your computer, could charge something else. Each of your devices may want different voltage levels. Right? Some of them may want 5 volts, some of them may want 12 volts, right? Depending on what they want. Right? So by then, if you have an electronic switch, right, by controlling T on, by controlling how often you're on, you can actually change the voltage level your load wants to see. Okay? So if you have a load that wants 5 volts, you can switch it at a T on, that's give you 5 volts. Or something that's on 12 volts, switch at a leave it on for longer, so you have achieved 12 volts. Right? So this switching gives quite a bit of flexibility on this kind of things. Okay? So you can do just by changing how often you close and open the switch, you can supply all types of different loads. Questions about this? Okay, so switching is really useful. Switching is really useful. If you did not have this switch, or if this was not electronic, then it's much harder to complete this. So one reason the voltage levels in the bulk transmission grid is only set at specific levels is I need to know the values to design transformers and transform between specific levels. Whereas here, since T-on is often actually software controlled. If you're doing embedded system, this is software control parameter. Right? So it's very easy to change. It's quite flexible in that regard. So this is similar to energy as power, right? So if you look at the energy consumed, let's say E is energy. This is also similar to that. The energy you consume is simply a fraction of the energy you would have delivered if you did not have a switch. Okay? So this is an important number. This number is very important. So this is called a duty ratio or duty cycle. And then often you see this written as K equals T on over tau. So this just tells you the fraction of time that you're on compared to the entire period. Any questions? All right, so just get a feeling of some numbers here. Right? So what do you think tau is in practice? Let's say you look at your adapter. Let's say your computer has a lot of this kind of DC to DC converters in it. How fast do you think they're switching at? What is on average the value of tau this period? Any guesses? Is it in the seconds level, milliseconds, microseconds? What is a reasonable number for tau? So if you look at the duty ratio, it just divides out, right? So you only care about the ratio of Ti and tau. But if you think when you design the circuit, you have to think about how long tau is. So any idea of how long 1 over tau is, this frequency? Let's say in your computer or in your phone. Any guesses what this number is? So it's not nanoseconds. It's not nanoseconds. And it's not megahertz yet. We're trying to put megahertz, right? So this is, again, we're very different. We're not quite there yet. We're not the processor speed, for example. We're not gigahertz switching. So this is roughly about, say, 10 kilohertz to 100 kilohertz. This is roughly today you have this kind of speeds. This is the switching frequency we operate at. So if you're interested in learning more about what the right switching frequency is, or why we engineering, how do we actually come up with this kind of switching frequencies? I really encourage you to watch the seminar from last quarter by David Perot. It's a Professor David Perot from MIT gave a very good seminar about how to think of power electronic switching frequencies. It's a quite interesting seminar there. So you want to watch that, an interesting one to learn more. So there are definitely benefits to switching fast. So similar to a VRSI circuit, you want to switch reasonably fast. You do not want to switch too slow. However, when you switch fast, you run into a lot of challenge as well. So how do you push this switching frequency, say, towards the very high frequency range for power applications? As an open question, you can make a lot of money by getting a higher switching device. Right? So this is something to think about. Okay, so Later we go to more detail, I'll point out why does the switching frequency matter. But if you're interested, go watch the seminar by Professor David. So it's a really good seminar on this kind of switching frequency. But for us, often we boil down to look at one ratio. But keeping back your mind, somebody needs to come up with tau, how long tau is. Right, any other questions for this? Okay, so if you look at this switching frequency, right? So you look at the devices, so what are they, right? So again, as we said, our things are not small, right, for hardware. Right? So where you see people say, oh, I have a, right? So if you look at a lot of LSI product, is I have a chip, with several billion transistors on it, with the size of a quarter. Here, our devices are size of coins. Right? So these are big devices. For example, a diode. You will see a diode. You will see a power diode. Right? So this is going to be discrete devices. And we're going to start off by looking at diodes. Right? So they're made very differently, but still our basic things are diode, transistor, and something called SCR. So let's look at the diode first. So a solid state diode, we all seen this diagram. So I'm hoping we have all seen diode. Right? So I'm assuming this correctly, right? Who has not seen a diode before? Okay, so I'm assuming that you have all seen diode and transistors until you tell me otherwise. Okay, so we'll cover how transistors work. We'll go to some detail of how transistors work. But I'm assuming at least this is not the first time you have heard of diodes and transistors. Okay. This is called a diode. We have a current going through the diode. So this is called an anode side of the diode. This is called a cathode of the diode, right? So positive and negative, or plus or minus polarity. There is a voltage drop across the diode. Anybody know what the material makeup of a diode is? How do you make a diode? You're doping silicon, right? So which has doped more, right? So there's two parts to a diode. What's the anode part and what's the cathode part? Am I remember this? Okay, so this is right phosphorus. So you have a p-n junction, right? Diode is the p-n junction that we have. So what this p-n junction allows us to do is basically, if you look at the voltage measured with this polarity, what happens is you look at the current versus voltage, this VI curve, then the forward bias region, you need a little bit of voltage difference, then this shoots up really quickly. Right? This is called the forward bias. And then you have a reverse bias region. So ideally, you should stop all current flow, but it's not exactly zero for the diode. So our diode does not exactly stop current flow. So you have a little bit of current flow. I have a little bit of current flow. That's called a reverse bias. Right. So what happens if you push too much voltage? Right. So if you look at reverse bias, if the voltage across the diode is too large on the reverse bias direction, then what happens to the diode? Right. So you got to do a breakdown voltage, right? So if it's too large, then this whole diode breaks apart and you don't have a diode anymore. Okay. So whenever we have a diode in the circuit, one thing in practical design you should always be careful about is you don't break down the diode. Okay, make sure your diode is spiked, right? It's large enough to not break down. Right? So that's why our diodes are this big. You don't want the diode to break down. Okay. over, for example, our voltages are, kilovolts. You'll see kilovolt ranges for voltages, right? So you want to make sure your diode can survive that sort of voltage. And then often for the forward bias, you'll see this sort of 0.7 volt drop. Right? For us, 0.7 volts is almost never important. Okay, so if you do VLSI design, then 0.7 volts is significant. A lot of applications depend on this 0.7 volt forward bias, right? But for us, we don't. 0.7 volts is not going to matter when you're talking about hundreds of volts at least, right? We talk about tens and hundreds of volts. Okay, so for us, we'll pretend the diode just turns on immediately once it's forward biased. Right? We'll often ignore this 0.7 voltage drop. Okay. Any questions about the diode? Okay, so this is our diode. This is our diode. Then, of course, this is our diode. Then we also want to talk about transistors, right? Transistors are our switches we're using in the circuit. Okay, so we want to talk about both diode and transistors. So then for a transistor, they're again not small. Okay, so if you look at bipolar transistors, you'll see them, right? You'll see this kind of bipolar transistor. They're fairly large transistors. Okay. And these are just NPN junctions, right? So you have dope, you have N with P in the middle, you have N. So we will use bipolar transistors often, whereas most other applications we use MOSFET. But for us, we'll use bipolar. So are there people who have not seen at least sort of briefly bipolar transistors before? Are there folks who's seeing this for the first time? Okay, so all right, so let's go through bipolar transistor then. So I'm guessing a lot of you have seen MOSFET, but maybe not bipolar transistors. So bipolar transistor compared to MOSFET, there's a difference as bipolar as a current-driven device. Okay, so the gate, right? So the base, whether this is an open or closed switch, is driven by the current. Okay, so this is the current control. Whereas MOSFETs are voltage controlled. So for MOSFET, you apply a voltage as the gate control whether it's open or closed. For bipolar, what you can think of as this is roughly a switch like this. And how you control whether this switch is open or closed is through this base current. Okay, so if you inject a lot of base current, you close the switch. If your base current injection is small, you open the switch. Right, you open the switch. So the idea is, I want to pass some current, IC. This is a multiple of the base current, right? So I'm operating, I have a gain factor beta. So I have a base current, then I multiply this base current by, say, by a factor, and I can control how much current flows from the C to E, from the collector to the emitter. So the terminology is not all that important. It's from C to E. How much current can I flow through this transistor? Okay, so basically the current I get is I get some of the current that's coming from the base, then plus a lot of the current that's coming from C to E, that the switch is coming across the switch. So at the end of the day, the current I get is the sum of the two currents. And then of course the voltage drop is right, so it's the sum of the voltage drop is from C to B, B to E, same as from C to E. Any questions so far about this bipolar transistors? Okay, so this is our bipolar transistor. Then what we care about is often always is, how does my current respond to voltage, right? So I have a switch. This bipolar transistor is not an ideal switch. right? Because it's not like, if you apply a little bit of, apply no current, this thing is off, a little bit of current, this thing is off, right? So it's not ideal. So let's look at a little bit of the characteristics of this transistor. Okay, let's look at the characteristics of this transistor. Right, so what happens is we want to look at is, still on this page. So these are all this voltage drops we can look at here, right? I have VCB, VCE, VBE, and I have some current that's coming in to the base. Right? So B stands for the base, C collector, E is the emitter. Okay. I have some current coming through the base, and to see how does the current relate to the voltage. How does current relate to the voltage? So this part from B to E looks like a diode. Because this is a PN junction. Okay, so this looks like a diode from B2. Okay, so what you do is, so if you have some VBE, if you have some voltage, then you can control the current, right? So as long as this voltage is high enough, then I can pass current through this space. I can pass current through this space. Okay. So then if you look at the amount of voltage you get, right? So if you look at the VCE, how much voltage I get across the switch, right? If you look at, voltage versus current, then what happens is if you look at VCE versus IC, so the way to think of this is our bipolar, we want to say this is approximately a switch. So this switch, you're looking at a voltage of VCE and the current of say IC coming down this way. Okay, so this is approximately a switch. We want to look at how close is this thing to a ideal switch, right? How close is this thing to ideal switch? Any questions right now? Any questions up to now? Right, so I want to see, if I pass, right, depending on, right, so I want to see how does this look like a switch, depending on how I operate the base current, right? So this is, so first let's look at the closed. So this is called the cutoff region. And this region is when the cutoff region. And this is region when you have the base current being 0. Okay, so if you do not apply any current to the base, then my switch looks like an open switch. Right, this is open switch. Okay, so nothing happens. You can push, you have very large voltage across the two ends of the switch. No current will flow. Right, so this looks like an open switch. This looks like an open switch for us. Okay. So then, how do we turn this on? Right, we want to turn this thing on. So if you, how do you turn this on? As you increase IB, right? You increase the amount of current you put to the base. This tells you the bipolar transistor, tells the semiconductor, now it should start conducting, right? It should start to conduct current. So then we get something called this is called the linear region. Okay. What happens here is as you have more and more voltage, you have more and more current, So look like a resistor. So this is the linear region. You can turn this is now a on switch that's on with some resistance, right? With a little bit of resistance. Then you can increase this more, right? You can still increase IB even more. Then what you get is so-called a saturation region. You got a so-called saturation region. This is where when we have, when you're already conducting a lot of current, we conduct a lot of current. So by making the voltage larger, you cannot conduct more current. So you saturate your transistor. Okay. So there is an off region, right? Cutoff region means just an open switch. Then when you try to close the switch, by injecting a little bit more current into the base, conducts current better until it reaches saturation means you cannot push more current through this transistor. Okay. Any questions so far?
So when IB is 0, that means the switch is open.
Yeah.
Saturation region, switch is closed, right?
Saturation means the switch is closed, but it's not a perfect switch because you're limited on the amount of current you can push through.
It's gonna be like the max current pass.
Yeah, you get to a max current. Yeah, so it's not a wire. It doesn't exactly act like a wire. Yeah, at that point. Okay.
And the linear region will be a switch closed as well.
Yeah, be a closed switch. That'll be like more like a wire with a resistance. Right? It's like a resistor. It's linear. Voltage and current are linear related.
Okay, perfect. Right.
Okay, yeah. So this is our switch, right? So it's not an ideal switch. It's not an ideal switch. And the reason we care about the fact this is not an ideal switch is you need to be careful when you operate a bipolar, right? You need to be slightly careful when you operate a bipolar transistor. Okay. So the reason you want to be careful, and we're not going to go into any type of semiconductor physics or anything like that. We just want to make a point that when you operate a bipolar transistor, make sure you operate at the correct region. Okay, there is some region you want to avoid when you're operating a bipolar transistor, right? So let's take a closer look at our transistor. Okay, so here I have something like, right? This is again IB equals to 0. This is a closed switch, and then I have something like this is IB max. This is the maximum. So when I go into saturation, this is the maximum amount of current I want to push through this. This IB max. Right? So what does this look like? Right. So let's look at what happens, let's say around this called 0.1, this 0.2. So at 0.1, at operating 0.1, what happens is I see, right, if you have a circuit like this, this is almost acting, you're pushing a lot of current through this. This looks fairly close to an open switch. So this is VCC over RL. Okay, so there's not much voltage drop across VCE. So this is a closed switch. And at 0.2, this is VCE is very close to VCC, meaning that there's no current flow. So I see roughly 0. So this is a open switch. Okay. So it's repeating what we said before. As you can get open and closed. You can get open and closed switches by determining how much current you push to the base, right? So we get to control the base current. We get to control IB. And by controlling IB, I get to control how it should operate. Okay, I get to control how it should operate. Right? So what happens in this region? Right? What happens in this region? It turns out is do not operate here. Okay, don't operate here. So it turns out we want to avoid linear regions. Linear regions are not good regions for power transistors operating. Okay, so power transistors operate either at the cutoff region or the saturation region. So let's see why. Let's see why it's not a good idea. So for the rest of the class, we'll see why it's not a good idea to operate at the linear region. Why would we want to avoid operating at the linear region? Okay. Right, so let's say we do this example. Let's take this circuit as an example. So we're saying, right, so we can either operate at the saturation region 0.1 or the cutoff region 0.2. So as a reminder, 0.1. So our 0.1, this is saturation. 0.2, this is cutoff. Okay, so we want to compute, if you pushing current through the resistor, there'll be some losses. Let's compute what the losses when it acts like an open switch and what the losses when it acts like a closed switch. And also we want to look at what the loss is if you operate at the linear region, right? So what if you operate in between this? I want to see why you want to avoid operating as a linear region. So is the question clear? Is the question clear? Okay, good. All right, so let's do some calculation. Right, let's say let's say loss at 0.1. Right, so recall 0.1 as the saturation region. Right, let's look at how much loss we're having here. So the total loss. So where are the loss coming from? Right, where are the losses in the transistor coming from? So the total losses we have in the transistor, this is we have base loss, right? So I'm pushing current this way, so they have some loss here. And then I have some collector loss, right? Because I have some collector loss because I have some voltage drop. Some voltage dropper cause the conductor. Okay? So my base loss is current times 0.7, right? This is IV loss. This 0.7 comes from, we have a diode. From B to E. Okay, so the space loss, this looks like a diode for us, right? So we have this diode, that's where the 0.7 voltage drops come from. That's why we have, pushing 2 amps across 0.7 of voltage drop. That's one source of loss. Then the other loss is the current, right? I'm pushing through multiply by the voltage drop I have across this transistor. So my current, this is beta times IB. This is 100 of the source voltage, subtract this value, subtract off the voltage I get across, subtract the voltage I got across the load. Okay, subtract the voltage I got across the load. Okay, all right. So this load voltage drop, this is 4.9 times 2 times 10, right? This is my voltage drop across the load. If you sum all this up, you get about 21 watts. Okay, you get about 21 watts of loss. Any questions for this calculation? So I have two sources of loss. One is the diode loss. I have some diode, we're losing power there. Then the other is you look at the current times the voltage drop across the transistor. Voltage drop across the transistor is the voltage drop of voltage as the source minus voltage dropping over my resistor, my load. The rest of the voltage is across the transistor. And you get, multiply them out, you get the loss.
I have a question
Right.
about the circuit.
Okay.
What do the two circles represent under IB?
Oh, two circles, this is a driver. So this is the current driver. This is where something has to send current. So this is, you can think of this as a current source that's sending an IB max. This is a current driver. This is a current source that's sending current. That's a good question. Any other questions? Okay, good. All right, so then let's see what happens. Then let's say at point 2, right? At point 2, IB equals 0, so there's no loss across a diode from the base to the emitter, right? So this B to E is there's no loss. And we're told in the question, assume VCE equals to 0.99 VCC. Right? So this is 100 volt, this is VCC. So then how much power are we losing? Well, my total loss is the current, right? The current, there's still some current flow multiplied by the voltage drop across VCE. And this is my loss across the resistor. So how much does current flow? Well, I have the source as 100 minus 0.99 times 100. This is my voltage difference across the resistor. So divide by 10, this is my current. Multiply by 0.99 times 100. This is my voltage. And then we get 10 watts. Right? So if it is a transistor, if the transistor is open, it doesn't mean there's no power flow, there's some power, right? Because it's not a perfect open circuit. But no, the power is fairly low. Right? Power is fairly low. And the reason we want to avoid operating at this linear region, right, at point 3, is because at this linear region, your loss will be very, very high. Right? So the reason is you want really to avoid this region. Okay? Because if you're operating at this region, what happens is, if you look at the total loss here, this is still we have IB3. So we have 0.1 times 0.7. This is a diode loss. This is a minuscule diode loss. This is not very important diode loss for us. However, recall that IC is beta times IB. Right? So here we have beta is 50. Okay? So then the rest of the loss is actually quite big. At 50 times 0.1, this is how much IC I'm pulling in, how much my transistor is pulling in. So this is, good current. And then I have a very large voltage drop. I have a fairly big voltage drop across this. Right, so this is my VCE, this is my IC, and you add this up, this is 250 watts. Okay, so this is a very large loss for a bipolar transistor. So this says that power transistors cannot operate at the linear region. Okay. So when you're designing your gate, when you're designing the current that's driving your gate, be careful not to operate your transistor at the linear region. If you operate at the linear region, you have a very large loss. Okay, you either want to saturate your transistor, making it very close, right? Making it, as looks, you want to saturate, right? Pull as much current as you can, or you want to operate at as an open switch, as an open circuit, okay? To avoid having a very large loss in this case. A transistor operating at a linear region will result in a very large loss. So if you look at advantage and disadvantage of the bipolar transistor, the advantage, this is very robust actually. This thing tolerates heat and loss and high current, high voltage quite well. It's a lot more robust than a MOSFET. It's a lot more robust than a MOSFET. Right, this is high speed. You can switch at a fairly high speed, high robust, high speed. But then the disadvantage is this is our high losses. And then requires a current-driven device. Often we prefer voltage driven rather than current driven. Often it's easier to drive something with a voltage than a current. But still, for power applications, we often use bipolar, but we're transitioning more and more to MOSFET actually. So today you'll see more people transition to MOSFET, right? And so if you use bipolar, if you have, you say, even for a closed switch, for open switch, you're losing 10 watts. For some application, this is okay to lose 10 watts. But then for some application, losing 10 watts for open circuit is not acceptable, right? So you don't want to lose 10 watts there. So then people are moving to MOSFET. But MOSFET is, in some sense, less robust. You have to be more careful about design. Whereas bipolar is just buy off-the-shelf bipolar transistor. You can plug into the circuit. As long as you avoid the saturation, avoid the linear region, it works. All right, so this example is basically, this example question is the level you need to know for bipolar transistors. So in the next homework, you'll do questions that are fairly similar to this, to look at what happens when you, to compute the losses and again reinforce that you don't want to operate at the linear region. Okay, you want to fully open or fully close your switch if you're using a bipolar transistor. Any questions for this? Okay, so as we go forward, often we'll draw a switch. We'll assume it's the ideal switch, because for our applications, often the power comes out to be in kilowatt range. So 20 watts, 10 watts, we don't worry all that much about this loss. But you should be aware there's some loss across the bipolar. The loss can be a lot higher than a MOSFET device. Right, so if no questions, we'll end here today. Right, as a reminder, homework is due tomorrow at midnight, and a new homework assignment will be posted tomorrow morning. Right, so again, reminder to look at the lab software for the lab. You haven't started already, right? So then I'll see you next Monday. Thanks, guys.
Are there going to be office hours tomorrow?
I believe TA Yao has an office hour, right? I believe Yao has office hour, so you're welcome to go to that office hour if you have questions for homework. You can also email, email all three of us, right? When you email, just send an email to all three of us. There's a better chance one of us will see the email in time.
Thank you, Professor.
Right, thanks, guys.